For a function to be self-inverse, it needs to satisfy two conditions. The first one is that f of x has to equal x, and the second one is that the inverse of f of x has to equal f of x itself, hence the name self-inverse. And in order for a function f of x to be classified as self-inverse, it needs to satisfy these conditions for all values of x in the function. And I've written some examples of self-inverse functions here below. And in order to check if a function is self-inverse, you just check if it meets both of the requirements that I talked about above. So we can test all these. Let's start with the first one, f of x equals x. First thing we do is check what f of x is, and that's just f of x, which is x. So that works. And then we check what the inverse is, and we just flip it around. So x equals f inverse of x, which is equal to f of x. So that works. And next one is f of x equals 1 over x. First, we check f of x, which is just 1 over x, and that is just x over 1, which is x. So satisfy that requirement. And then we check the inverse. So x equals 1 over f inverse of x, and then f inverse equals 1 over x, which is equivalent to f of x. So that also satisfies both requirements, meaning that it's also self-inverse. And now let's test the last one, f of x equals negative x plus c. First, we find f of x, which is negative x plus c, and this turns into x minus c plus c, or x, so that works. And then we check f inverse, so x equals negative f inverse of x plus c, and if you move things around, you get f inverse of x equals negative x plus c, which is f of x. So that also meets both requirements, meaning that all three of these functions are self-inverse, and I just showed you how to prove that they are. And on a graph, all self-inverse functions have reflective symmetry over the line y equals x. And this means that if you reflect them or flip them over that line, then nothing's going to change, and it's going to stay the same. And I drew an example here. This is a self-inverse function, and imagine flipping it over this dotted line, which is y equals x, and nothing's going to change, it's going to stay the same, and that's the same for all self-inverse functions. I know I said at the beginning of the video that there are two conditions that need to be satisfied in order for a function to be self-inverse, but in reality, if one of the conditions is satisfied, then the other condition is always satisfied. So let's look at this condition. This is the first condition that I talked about, f of x equals x. And the definition for an inverse function is that if you have a function f of x, then f of the inverse of f of x will equal x. That's just a definition of the inverse function. It undoes the original function, what it does. But if both of these are true, and this one always is, then that means f of x and inverse of f of x are always the same. So we can also write this if both are true. And this is actually the second condition that I talked about, meaning that if this is true, then this is true. And if this is true, then this is true. So you only need to prove that one of them is true, because if one is, then the other one always is. Now let's do a practice problem. If you think you can do this one, then pause the video and try it. This one says, show that f of x equals 7x minus 5 over x minus 7, where x doesn't equal 7 is self-inverse. And like I said, you only need to prove that one of the requirements is true, because if one is true, then the other is true. But just for the sake of the video, I'm going to prove both. So for the first one, f of x has to equal x. And first, let's find what f of x is. We can rewrite this as f of 7x minus 5 over x minus 7, which is 7 times 7x minus 5 over x minus 7 minus 5, all over 7x minus 5 over x minus 7 minus 7. And then now we just need to do some algebra to simplify this. We can multiply both sides by x minus 7 to get rid of the fractions, and we get 7 times 7x minus 5 minus 5x minus 7 all over 7x minus 5 minus 7 times x minus 7. And now we can expand all of these, and we get 49x minus 35 minus 35, no, 5x plus 35. And then for the denominator, we get 7x minus 5 minus 7x plus 49. But then now we can combine all like terms. So minus 5x goes into this 49x to get 44x. And these 35s cancel out. 7x minus 7x is 0. And then the negative 5 and plus 49 become 44. And then now you can see that this is simply equivalent to x, which is the condition that we satisfied. So there. Now you've proved that it is self-inverse. And now I'll do the method where you prove the second condition, which is that f inverse of x is equal to f of x. And first we need to find the inverse of f of x, and for that we can just flip around the f of x and the x. So we just write x equals 7 times the inverse minus 5 all over the inverse minus 7. And this one might seem a little hard to simplify, harder than the last one at least, but you can just multiply both sides by the denominator, and you get x times f inverse of x minus 7 is equal to 7 times f inverse of x minus 5. And then you can distribute the x into both, so x times f inverse minus 7x is equal to 7 f inverse of x minus 5. And then now you can subtract 7 times the inverse function to both sides, and on the left you get x minus 7 times f inverse of x minus 7x equals negative 5. And then you can move the 7x over to the right side, and you get 7x minus 5. And now you divide both sides by x minus 7 to isolate the inverse. So f inverse of x equals 7x minus 5 all over x minus 7, which is f of x. So now you've proved that the inverse function is equivalent to f of x, which means that it is self-inverse. And sometimes when you do this, your resulting answer, which we got here, is not going to be like algebraically equivalent to this, but when you graph it, it still might be the same. So even though your answer that you get here might not look the same as what you get for f of x, just check it on your graph calculator if you can, and if they line up perfectly, then that means it's equivalent, which means that it's self-inverse. So everything that I explained in this video and all the problems that I went through should teach you everything you need to know about self-inverse functions. If you learned something from this video, or if you enjoyed it, please consider liking and subscribing.